Okay, folks, we're going to get started here in just a moment. Maybe a few quick announcements. So welcome to day 8. Does that sound right? Okay, day 8. Man, we are really into this. We've got today, tomorrow, and then the next day is a half day. I think we talked about this on Friday. I did want to confirm that I checked this morning with the buses. They, again, you will, when you leave your dorm on Friday, put all your luggage on the bus, and the buses will keep that there while we have our morning session on Friday, and then you'll get back on the same bus Friday morning, and it'll take you to the airport. If you're one of the few people who are not going to the airport, check in with Teresa. She'll be able to help arrange the location of your baggage so that we can make sure it doesn't go to the airport without you. Let's see, this morning, we have 2 lectures in the morning. One is from a young, dashing, brilliant scientist. The other one is me. But we'll have a break in between of those. Then we will have our lunchtime session. And then in the afternoon, we'll go to classes. There is a bus going up to SNS. That is for the neutron scattering students only. And that is for students who have already been assigned a neutron scattering class. I know that's a very popular class, but we can't have you moving around, especially when you're being on the bus and changing locations, because we have to be able to track you. So please go to your assigned classes. Let's see, what other announcements for today? One thing, Nathan, where are you at? Nathan, I know you're here. Okay, maybe Nathan's not in the room at the moment, but he came up to me and was talking about, are there ways that we can keep this community together after summer school ends? And there is a Discord server. I know that some people are using this. In fact, I think a lot of people are. And Nathan and a few others are putting together a plan to sustain the Discord server, at least for the next year before the summer school in 2025 starts. So if you're interested in supporting Nathan and that team on this, please check in with him. There he is now. Okay, there's Nathan. So check in with him and he will give you the latest news that they have on this. Basically, the idea is that you all have remarkably come together relatively quickly across many different disciplines and institutions. We don't want to throw that away. We want to sustain that. We want to keep that going. So I'm happy to help. I think all the 5 centers will be happy to help, but we need your participation to make it worthwhile. Okay, any questions, comments, concerns? Complaints are in the back. Okay, complaints back there. Now, Ria, what's up? Say that again. I didn't say anything about a Frontier tour. So, okay, I've gotten multiple requests about taking a tour of Frontier. We haven't been able to figure out those logistics yet. So on Thursday, tomorrow, one of our speakers fell through in the late morning session. This is Joe Carlson from Los Alamos. He's going to talk about nuclear physics. Travel constraints got in the way of that, but we've got a little bit of time in there, about an hour and a half. So we were trying to figure out what do you do best with that time. We have found someone at Oak Ridge and Sherwood to come in and talk to you about all the different opportunities that the Department of Energy has for students to get involved in research. And that's another question that I've gotten. In fact, I think that one's even more popular question. In addition, we're trying to see if there are opportunities to walk over to the OLCF where we house Frontier, give you a short, quick tour of that. It's a very popular site. We're asking very late, and we're a very large group. So we haven't figured out the logistics yet. So, but if we do get updates on that, you'll be the first to know. Okay, any other comments? Okay. Well, then let's get the show rolling. I'll start us off this morning by talking about something that I'm really interested in, and that is integrating quantum computing into high-performance computing systems. A lot of people have asked me, you know, Travis, what do you actually do? It was a very, very well-meaning question. I do research. In fact, one of the things I'm most interested in is how do we take something like a high-performance computing system and merge it with this quantum technology that we've been talking about. So I want to expose you that to today. I'm going to specifically focus on these 3 topics, right? These are the 3 things I want you to learn when we're done here. One is why would we do that, right? Two, okay, if we do that, how do we talk about it? What are some of the terminology and techniques for quantum HPC? And then three, where's that challenge at? Where's the priority research that we should be focusing on now? And three is where I spend a lot of my time, but the other two are equally important. And so this talk will have a lot of that in there as well. So we've heard a lot about motivation for why quantum technologies are interesting. This is my personal viewpoint on it. If we're talking about high energy physics, or we're talking about superconductivity, or we're talking about catalysis, chemical reactions, every time we talk about these things, we have to use the language of quantum mechanics to have the most accurate and precise description. And fundamentally, that's because nature itself is quantum mechanical. This has been the revolution over the last 110 years that pointed out that the evidence that we see at the very small scale contradicts classical mechanics. Now, it also plays a major role at the very large scale, though. So if we're talking about things like the sun, where high energy collisions are occurring all the time, including exotic particles, if we're talking about superconducting distribution of energy, or we're talking about how to create sustainable environments, all of these processes at the top immediately have consequences. Our ability to understand and master those are essential to pushing forward our species. Now, here at Oak Ridge National Laboratory, we're actually working on all of these problems. And I don't know if you guys have seen this aerial view yet, but all of this is part of the National Laboratory. So all these trees. This part right here is where we're located today. Up there is the spallation neutron source. That's where we've been a couple times now. This building you see right here, there's the pond back there. We're actually about where that little green dot is now in this conference center. This big white building here, actually it's a collection of buildings. That's where we house the high performance computing systems. So that's where I want to start the story, because those problems and the science that I was just talking about is fundamental to what this laboratory does, and in fact, all the DOE's national laboratories. But for us in particular, high performance computing has been an essential part of how we try to understand the world around us. It's great for modeling and simulation. Having the biggest, best, fastest, most super machines in the world have been part of what defines Oak Ridge National Laboratory's mission for scientific discovery and energy security. So what you're seeing here are three systems across almost over a decade of time, representing massively parallel computing architectures. And what I mean by that is all of these cabinets that you see here are filled with computer chips. And the way we use these systems is those computer chips all operate concurrently at the same time, processing information, performing calculations, and it's the result of that concurrent process that leads us to an answer. And what you'll see is that as you go through the years, the amount of performance measured here by number of floating point operations per second is increasing. In addition, you'll notice that the power is also increasing. These are the best machines in the world. These is the fastest you can do calculations, but also in some sense, the most energy intensive calculations that you can do. Now, when you start to look at these systems, they're made out of things like a node that you see here. This comes from Frontier, the current #1 computing system in the world, located here at the building I was just pointed out. It's made out of over 9,000 of these nodes. Each of the nodes corresponds to a CPU connected to 4 GPUs. And this is actually based on a technology by the company AMD. The GPUs themselves are interconnected with each other. You can share memory and information. You can program them to perform calculations. That complexity is part of what makes the machine so remarkable, is that you have control over a very large number of resources and can get up to 60 gigaflops per watt. So that's a pretty good number in terms of operations per energy usage. When you look at the infrastructure that's required here, you can see this is a close-up view of the cabinets with the doors taken off. You can see all the connections that are being made on here. Here's a view of the type of cooling required to keep these systems from overheating, as well as the water that's flowing through that infrastructure in order to keep the temperature down. It's a massive system. You saw in the building that the room we're in is pretty big. The building that's housing this system is 3-4 times the size of this. Yeah. Yeah. Okay, fair point. Yeah, so right now, this is about an exaflop. So that is, thank you, 10 to the 18 operations, floating point operations per second. And by comparison, the computer I just got at home, I think it may be around 10 to the 12 floating point operations per second. That's my best guess. I'd have to work through but this is a million times better than any laptop you have, right? So that's my back of the envelope thing. Oh yeah, 10.
Like the cost.
Yeah, sure.
Will we see like any like better, like will you produce better computers?
Absolutely.
Like,
so if history is a prediction of the future, then yes, we are continuing to do better. We're continuing to see the number of operations increase. We're continuing to see the technology that makes up these devices get smaller. So when people talk about Moore's law and transistor size decreasing, part of that's because you want to be able to put more transistors into these devices so you can do more logic, you can reduce the amount of voltage that they use, and you can basically do better. But
if you expand the system, the supercomputer more, you're gonna use more and more power. And so I don't know if like those coolers will like handle that.
Yeah, excellent question. So as these systems get bigger, they use more energy. That energy dissipates more heat. You now need more energy to drive the cooling process itself. So you can do better, but it's going to cost you.
Yeah,
it's going to cost you. It's going to be a trade-off. That's right. So that's why that question is a little open-ended. That's why it's easy to say yes.
Yeah.
Because if you don't constrain me on anything else, I can always do better. But if you tell me the local Tennessee region only produces so much power, right? Or I only have so much space in which to install this system, or I only have so much water that can flow through at any given point in time, then there's limits on how big of a system I can make. Man. Is it index-based? Oh, Linux-based. Actually, I think it is proprietary or a custom. Let me say not proprietary, but a custom operating system. So there's a lot of different kernels and these types of things that have to be written for it. So, but I do think it may be Linux, starting with Linux. Now, what do we use those machines for? Here's a breakdown just in terms of the types of problems that are typically run on these types of HPC systems at the national laboratories based on the amount of time spent on those problems. And what I want you to notice is that physics, material science, astrophysics, biology, chemistry, easily 3/4 of the amount of effort that these machines are putting forward. All of those problems depend on quantum mechanics. And if I'm being really clever, I can tie engineering and earth science to it as well. But fundamentally, the reason I'm building such big machines is so I can solve quantum mechanical problems. Now, go back to that original slide. The reason I want to solve quantum mechanical problems is that describes our universe. That describes everything around us. It describes the technologies that we're trying to develop. It describes what's important for our society moving forward. So this is being used for public good to understand at a more fundamental level how all of these different topics behave. The reason we're having to solve these problems on those HPC machines, though, is they're very hard problems. They're not problems I can solve on my laptop. Not when I get up to the sizes and scales where I'm pushing the frontier of scientific discovery. So at this point, I want to call out something as a note. How many people have seen NB before? Yeah? Do you remember what it stands for, Hector? Do you remember what it stands for? Nota bene? Yes, exactly right. So a good note, right? I don't know if I've got the translation right, but there's a few of these in these slides, and it's intended to call out what I think are important points to pick up along the way. One of these is called Amdahl's law. And basically, Amdahl's law says that there's a limit on the amount of speed up that you can get from parallel processing. So I can build these massively parallel systems bigger, but whether or not that's worth it is actually predicted by Amdahl's law. And in Amdahl's law, he's saying, I have some process, some program that I want to run, and let P be the fraction of that processing time that could actually be parallelized. Okay, so maybe I'm trying to sort something. Maybe it's a deck of cards, and I'm trying to sort them into hearts and clubs and spades and diamonds. That's a difficult problem to do on your own. But if you and a friend cut the deck in half and then you each sort them, you can speed up the amount of time. But at the end, you have to then merge the two piles back together. That cannot be parallelized. So there is some fraction of the problem that can be parallelized, and we'll call that P. And then S is how much we can speed that up. Maybe it's the number of people who I'm cutting the cards in and sharing the cards with. And this expression, derived by Amdahl, gives you a limit on how much you expect to be able to speed up that problem, the original problem, if you have both P and S. Yeah.
So P is kind of like a number inherent in the problem, but S is something that you have control over.
That's right. So depending on the algorithm I use to solve the problem or the method in which I program that algorithm, the P itself will actually change. That's right. So my question then is, well, what happens as S, the number of things I'm using to parallelize with, goes to infinity? I'm making my machine bigger and bigger, infinitely big. Am I going to get an infinitely short processing time? No, that's right, Kevin. No, that's right. 5 points.
I don't know if he's like a.
So as S is going to infinity, this term is going to 0, and then I'm left with this fraction. And that fraction is basically what Amdahl's law is saying, is there's a limit to how much parallel computing can speed things up. So remember, these hard problems we're trying to solve, we're using parallel computers, these massive supercomputers, to solve those problems more efficiently, but we can't build them infinitely large and expect an infinite improvement. Yes?
Much about parallelization, but how easy is it to tell if a task can or cannot be parallelized by like any algorithm?
Yeah, so I'm going to get to something later called domain decomposition that touches on this, but you have to go back and look at the algorithm that you're using to solve the problem, and then also the architecture on which you're solving the problem. Both of those factors are going to contribute to this question of what's the value for P. A lot of it, though, I would say mathematically, is based on your intuition. You know, like we were talking about with the card cutting problem. Would you have known that if you and your friends got together and cut up cards and sorted them, that that was maybe a faster way of doing it than by yourself? You might have some intuition. You might think, yeah, we're sharing the burden. That seems like it'd be faster. But there's other problems where that's not quite as obvious. So, Miriam, yeah.
There's some kind of way for you to develop my algorithm to be able to be parallelized and other algorithms not to be parallelized, like how to think in a way that my algorithm is able to split tasks and work in that.
Yeah, great question. So the development of the algorithm, I would consider in the realm of mathematics, right? So what is the best method to solve a given problem? And if you're thinking about, well, I have available to me methods to parallelize it, maybe there's even a finite number of those available, this S that we're talking about, then I can develop that algorithm to take advantage of that. But it is not fixed in time. It's not determined by the problem itself. There's some creativity in the development of the algorithm that you have to include. Yeah. Please, yeah.
Which is something mathematicians use to quantify algorithms. you might have heard of this concept, but there is actually two computational complexities. One is called the work, which is what's commonly used, but there is another one which is called span. Work quantifies how much the computational complexity, say we have like a CPU base, which means that we can only compute one at a time. And the span domain is the computational complexity, say we have an infinite amount of parallelized computing power. So in that case, if you want to develop a parallelized algorithm, you should have an algorithm with a very small span compared with work. So there is a mathematics or like a different notion of mathematics.
Yeah, now the great point. So I'll talk a little bit later about domain decomposition, which is going to touch on similar idea. But developing the algorithm itself does require you to be thinking about these parallelization aspects. Now, I think we've seen this quote several times. You probably could cite it from memory. Quantum computing and quantum technology more generally also does a form of parallelization. Right? That's when we think about superposition, when we create these superpositions of our computational basis states, so 0 plus 1. Feynman's idea here was, we really care about simulating nature. It's important to our understanding of all of these things around us. We're building these computers that are used in classical technology. There's a mismatch between the model of the system that I have, which includes things like superposition and randomness and measurements that project things out, and classical devices, which do none of that. And so his point, that we've talked at length over 8 days about, is that you need to adopt this mindset that quantum mechanics as a basis of technology can be developed in order to solve some of these problems in completely new ways. So the question earlier about how do I design an algorithm that can be parallel, that is in some sense embedded in my mindset of conventional computing, classical computing, that I'm doing things in parallel, but they're independent of each other when they're processing. With quantum computing, we know we have entanglement, we have superposition, and that creates correlations across events that are occurring. So I can apply operations to two things independently, but the fact that they're entangled means that their outcomes are still going to be correlated with each other. So it's going to change this integration aspect a little. Okay. Has anybody seen the block sphere? Yeah, you have. The right-hand side of this, though, is what I wanted to focus on, which are these 5 requirements that David DiVincenzo came up with well after Feynman's original conjecture. And these 5 things are basically what he said are the minimum criteria for a quantum system to be like a computer. The first one is that you want to have a scalable, scalable system of qubits. Sometimes it's called a scalable array. In the end, I'll refer to this as a register. It is the physical technology in which I am storing quantum information, and I can make it as big as I want. I can have n qubits. I have to have the ability to initialize those qubits. If I have a register or a memory, and even like a conventional computing program, I have to start off in a known initial state. Otherwise, it's randomness, it's noise. I have to have an ability in a quantum computer to project into that initial fiducial state. I love the word fiducial. It just means kind of like basic. I have to have a universal set of quantum gates. We'll talk more about that in just a second. I have to have decoherence times longer than gate operation times. And this is based on the fact that our physical system is interacting with its environment. It's not in isolation. And in order to perform any sustainable calculation, I have to do that faster than I lose information. And then I have to be able to read that out. And this measurement point is always a little bit confusing because it creates a dichotomy between classical information, which are the results of measurement, and measuring, which is a quantum mechanical process by which I project a quantum state into a well-defined outcome. But we have to have that to interface with quantum computers, to get real information out, for lack of a better word. Now, there's many different ways to implement those gate sets. We have focused a lot, I think, on digital computation. So that's the idea of circuit diagrams where here's my register and these are my fiducial states, all zeros. Here's a size state down there. The lines, of course, correspond to the lifeline of those registers. And then here are those operations I'm performing, and they're discrete events. And it looks a lot like Boolean logic. I have 2 bits and I XOR them or I AND them or whatever I do to them. The outcome of that then are these measurements, and that's what these little speedometer symbols represent. It's not the only way to do it though. Digital computation in some sense is maybe easier to parse or understand because it has this mapping into circuit diagrams that look like sequences of operations. But there's something called adiabatic computation. Carlton Coffran talked about this when he's mentioning quantum annealing. It's an entirely equivalent, entirely equally powerful method of computation, but it instead uses slow transformations of my register state. So I start off in a well-defined fiducial state, and then under a designed Hamiltonian, I evolve that system using Schrodinger's equation, but I do it slowly. There's an adiabaticity theorem that says if I do it slow enough, I will always stay in the ground state of the Hamiltonian, and then when I'm done, I can read that state out, and that will be the solution to whatever that final Hamiltonian's ground state was. And then something that's a little bit in between is this analog computation, which is also continuous transformation, but it can be much more fast. Much faster. And the point here is that real physical systems are undergoing fast transformations all the time with their environment, with themselves. Can we mimic that in hardware? And so these 3 models of quantum computation are all entirely equivalent, all equally powerful, can all solve the same amount of problems, some perhaps more naturally than others. Anastasia. Yeah, so the difference between adiabatic and analog. Here it is an emphasis that adiabatic is about slow transformations. So if I think about my time-dependent Schrodinger equation, and it has a Hamiltonian that depends on time, that Hamiltonian itself is changing slowly with time. So the derivative of h with respect to t is very small. So it's very slow change of h. On the other hand, analog computation does not have that requirement. It can actually have a very fast change in h. That could be like a laser pulse coming in and driving a transition in a physical system that's on a very fast time scale. Doesn't mean it can't go slow. It can do that in between, but it's not required to. Now, within those models, we know that there are many different types of algorithms that can be used to solve very interesting problems, including quantum simulation, which is in fact the algorithm of solving Schrodinger's equation. Literally run Schrodinger's equation. Do analog simulation just like we were talking about. Make a measurement, that tells you the outcome. Being clever about that, though, can be difficult. You can also use it for things like partition functions, so that's adding up summations, discrete optimization, machine learning, factoring. The other day, someone asked the question, if you had a quantum computer, what's the first thing you would do? And someone said, I would crack passwords. I just wanted to point out, that is illegal in most places. So I just wanted everyone to be aware that we do not advocate you creating quantum computers to hack passwords. There are government organizations that you can call if you need that help. But there's many other algorithms. But these algorithms then can map onto applications. And this is honestly where we come back to why do we have these quantum science centers? Why do we have the DOE national laboratories? Because we're trying to solve these hard scientific problems, and we want to use these algorithms in any of those computational models we were talking about as a way to try and do that more efficiently than the high performance computing systems we have today. Okay, so here's some working terminology. And I introduced this mainly to give you kind of a grounding and a basis for what these different types of algorithmic language can mean. So we've talked about quantum or classical algorithms, and what I mean here is just a defined sequence of transformations on my classical logic state, so my ones and zeros. Okay, it's defined ahead of time. It's not necessarily random. Randomness can be part of that algorithm, but the fact that the sequence is well defined is what makes it an algorithm. I can extend that then to a quantum case where now the transformations apply to a quantum computational state or quantum logic state, and the transformations themselves can be quantum operators, so the unitaries or the time dynamics that we've been talking about. And then a hybrid version of this is I just put those two things together. Now, when we were talking earlier about creating a fiducial state and making a measurement, the emphasis there is that at some point I made a classical decision about what the value of my quantum system is, either the beginning state or the final state. The beginning state was I said they're all going to start off at 0. I want all my qubits to be in the 0 state. How do you do that? How do you communicate that? That's classical information. Similarly, when I perform a measurement on the register and I generate outcome, maybe it's all zeros, maybe it's all ones, how do I communicate that? That's classical information. So most of the algorithms that you see today have some hybrid nature to them because there is an input and an output that defines this quantum classical boundary. Oftentimes, though, when we say hybrid algorithms, what we mean is that in the middle of the input and output, there was some feedback with a quantum and classical system that was driving some of the computation. There's also quantum circuit. We were talking about that earlier as a way to visualize these sequences, a quantum program, which is translating those sequences into instructions. These would be things that actually run on a device. An application, which uses a program to solve a specific problem, and then advantage, quantum advantage, which is the idea that that application can actually outperform some baseline program. And normally it's a classical baseline. And what's going to happen is we're going to talk eventually about how many people right now are looking for quantum advantage using quantum computing systems, and they're going up against Frontier. They're using Frontier as the classical baseline because that's the fastest supercomputer in the world. There are many different technologies. I think we've heard about all of these here. One thing I would emphasize is that they all have different energy scales, okay? And those energy scales are often unique to the technology. So ion traps are normally around megahertz energy scales, whereas transmon superconductors are on the order of gigahertz. It's about 1,000-fold difference between the energies there. That also means there's about 1,000-fold difference in the characteristic timescales for their dynamics. And that's going to show up when we talk about the decoherence and the operation times that are needed. And all of these are being commercialized at some level. I think you've probably seen these cute glossy photos from different places. It's exciting because the technology itself is now getting to a stage where we're seeing the number of qubits. That's first requirement, a scalable system of qubits is starting to increase. Here's a timeline over the last 20 years or so where the number of qubits that have been reported in the literature have gone from just a few to on the order of 100 or more. In fact, there's points on here that get up into the thousands with some neutral atoms and quantum annealing systems. So we're definitely headed in the right direction. But one of the biggest challenges for that is increasing the yield of manufacturing qubits that are very high quality. So the noise in these systems continues to play an important limiter on their performance. So to give you an example of this, we talked about initializing into a fiducial state. We know that this noise can corrupt the information that's encoded in the quantum register. That's normally by coupling to the environment. There's some nearby system, perhaps it's a spin or a charge, and it is feeling, your register is feeling those effects. It can happen from many other things as well, but oftentimes that leads to decoherence, decay, and leakage. And we'll talk about decoherence more in a second. But one simple way of trying to see that is to model the measurement of this register as a noisy process, where if I initialize it to the 0 state, the probability that I actually would immediately see 0 upon measurement is given by 1 minus P0, where P0 is that probability that it actually jumps out of the 0 state into the 1 state. And so it turns out that in most devices today, you'll actually see a distribution of these different probabilities. So I've got a P0 and a P1. These are all different qubits. They all correspond to a superconducting device that IBM put out. And what I want you to notice here is they're not behaving the same. I don't have a set of a register where all the qubits behave the same. It's not a scalable system because they all behave differently and I have to characterize them independently simply to understand what's the noise in there. Now, the question of how do I combat that noise is actually a separate topic that we'll come to in a second. But it's not just readout. You can also completely lose your information in your program prior to the program completing, and this is typically called decoherence. So this lifetime on your information may be shorter than the time it takes to do the program. So it's gone. Like you're still doing operations and there's nothing there except noise. And you can again see if we look at all the different qubits in one of these transmon devices and we measure these T1, T2 times, they're all over the place. So they're fluctuating. And again, it's difficult to use a system when you don't know how it behaves. Okay, so here's my next note to bene. What are T1 and T2? I'm not sure if everyone has seen this yet, but they are characteristic metrics for describing the performance of the register. And typically T1 is referred to as the relaxation time, whereas T2 is called the dephasing time. And to try to help you understand those different effects, over here is a single qubit density matrix. It's actually describing an initial pure state. And then it's undergoing relaxation and dephasing. The T2, you notice, is in the off-diagonal elements. So the coherence, coherence between the 0 and the 1 state is decaying with time, and the time scale for that is T2. On the other hand, the population along the diagonals given by the absolute magnitude, that's decaying with time T1. And in this particular scenario, this top left corner is the 0 state, so the energy is decaying out of the system and all that probability is going into the ground state. So when we talk about these characteristics of the register, what we're actually referring to are characterizations of the dynamics of the loss of information. Questions on that? Clear as mud? Good. Okay, now there are, of course, ways to mitigate these types of errors. Scaling up will eventually require some sort of fault tolerance design. That includes quantum error correction. We know if we redundantly encode information into the register, then we can use things like error correction codes and syndrome measurements to monitor the intermediate state of it. Oh, yeah. If I have a what? Oh, a toric code. Yeah. So the question is, if I have a toric code, is T1 infinite? No, because the T1 process itself, the relaxation process, is describing that physical system. So depending on the value of that, that's the time scale at which I'm losing energy and information. My coding, just like here, or in any error correction code, will itself have a time scale on which I'm checking to see, are you still there? Are you still there? Is exactly right. Yeah. So when I was talking about that in the last slide, that was at the physical level. Yep. So, oh, yeah. Yeah, so characterizing the loss of information, but not with complete energy loss. Yep, exactly right. So this actually ties a little bit into the error correction process, because with error correction, the point is that we know errors are happening. What we want to do is monitor the rate at which they're happening and then try to remove their effects. So in this sense, you can still have a decay process, decoherent process, but by performing error correction, you kind of catch it before it's completely gone. and then you can reverse to some degree the effects of the error to recover the original state. But there are limits on this, and this is where the distance of the error correction code and all of these other parameters become important. So it's not a simple situation where you can always do it, but under the right circumstances, there are ways to prevent complete loss of information. Okay. Now, there is an overhead with that, though. That redundant encoding means more qubits. It means more operations. It means that as I increase the distance of my code, this is the D that we were just talking about, I can get better performance. So depending on the physical error rate at the bottom, different codes can bring me down to a lower logical error rate. So that's the actual observed rate of error in my system. If I want to create a system that can solve some of the applications that we were talking about, I'm going to have to scale it up to millions of logical qubits. If each logical qubit has on the order of 100 to 1,000 physical qubits, I'm now on the order of 1 billion logical qubits to create a quantum computing system that is both fault tolerant and capable of reaching quantum advantage. That's a back of the envelope estimate. There's many ways to try to improve those numbers. You can bring down the number of qubits required for error correction. You can reduce the complexity of the problem you're trying to solve. You can try to do things in parallel. Okay, so we're talking a little bit about errors now, and I just wanted to make sure that we all understood how these things can accumulate. Because if I have a single qubit and I perform a single operation on it, I normally refer to the fidelity of the operation, the accuracy with which it transforms my qubit. Let's say it's a unitary. I have some idea what that unitary does. Maybe it's a rotation by a certain angle. The accuracy with which I rotate that qubit, that's the fidelity. More generally, though, I can think about the error that my gate implements on the quantum state. And let's say, just for argument's sake, I can describe it by a single number called P. I have one qubit, and I'm going to perform N gates. Each gate has a probability P of occurring an error. After I've performed all N gates, what's the probability that my qubit has experienced an error? So it turns out the way you can solve this is based on the binomial distribution. And this is the exact same distribution you use when you're talking about flipping pennies. Flipping pennies has got to be my favorite analogy. I think it's the thumb motion. Okay, but when I flip a penny and if it's a fair coin, it's 50-50 chance I get heads versus tails. If I flip the penny twice, then it's 1/2 squared probability that I see heads twice, and 1/2 squared probability I see tails twice. If I flip the penny n times, it's 1/2 to the n. So in a similar way, I can calculate the probability to see k errors after n events with an error rate p, and it's all based on this binomial coefficient, which we pronounce as n choose k. If I then want to know what the cumulative error is across these n events, that total probability of error, I have to sum up all the possible cases, all the way from 1 error to n errors, and that gives me my cumulative error. Okay? So binomial distribution is by far the distribution I spend the most time with. I know people like Gaussians, they're very integrable. But when it comes to the statistics of quantum systems, binomial distributions and their generalization called multinomial distributions are absolutely critical to understanding the errors. Okay, so we were talking about resource estimates based on error rates. So if I want to achieve a logical error rate of a given value, I can back out how many qubits and how much time my quantum algorithm will require if it has to be fault tolerant and it's solving certain applications. This is what our partners over at Microsoft have done. You can find the archive link here. When you click on the slides, hopefully this takes you to the website. I tried to make that a little easier. But each of these areas represents the amount of resources required to solve those problems. So it could be quantum dynamics. Again, this is solving Schrodinger's equation. It could be factoring. This is the thing we do to get put in jail. It could be quantum chemistry. This is the thing we do, you know, for the good of humanity. Whichever choice you pick, the fact is the time it takes to solve those problems is scaling on the order of minutes and seconds all the way out to decades. So some of these quantum chemistry problems, they estimate with current algorithms and system designs might take 10 years or more to solve. That does not sound sustainable, does it? Yes.
Like named as one of the most likely areas for quantum advantage in the near term.
Yeah.
Here it looks like that.
So great question. So the question comment really is, chemistry is often put forward as a great example of where we may see quantum advantage. So why does this look so bad, right? And one of the tricks about the chemistry is that you have to pick the right problem. There's been a lot of work that's gone into solving chemistry problems like electronic structure and these types of things using the HPC systems, and we've gotten very, very smart at that. There's enormously complex theories that reduce these molecular models down into things that are much simpler to solve. And the high-performance computers do that very well. And that's actually been driven in part by the presence of the high-performance computer. So if I told you, here's a machine that can solve these types of problems very well, you'll start to look at your problem and say, yes, let me change my problem into one that can be solved on this machine very well. And right now what we've seen is that in chemistry, the chemists have done a great job. So they're so smart. I'm a chemist, by the way. So but there are other problems that don't fit those machines well. And that's where we think the new opportunity is. Those problems are not being represented here. Things like chemical reaction dynamics, where you're going through like energy transitions that are at very high energy values. In those cases, the electrons themselves become entangled with each other, and it's very difficult to accurately model them with conventional theories. So now you have the opportunity to use a quantum computer to drive the development of algorithms for those problems. But this requires people to envision that a quantum computer exists and I can design algorithms that run on that. And so this goes back to the point we were saying earlier, the development of the algorithm depends on the architecture of the system you're targeting. If all you think you have is conventional computing available, even if it's the fastest supercomputer in the world, you will be limited in the type of algorithms that work well on that system. Quantum computing completely changes that. It gives you a completely new platform, a completely new architecture upon which you can take advantage of this. And we've only begun to scratch the surface of what are the best ways to do that. Okay, so what is quantum advantage? You can see in the diagram, there's this idea that as the problem I'm solving gets bigger and bigger, my conventional system, this blue classical computer's performance, maybe it's time. It could also be energy, it could be accuracy. There's many different metrics. This one's time. But the amount of time it takes is increasing, and this is quadratic or exponential. At some point, the idea is that my quantum computer, given by this yellow, flat, perfectly straight line, that's an approximation, is going to cross over. And the time it takes to use that quantum computer is now going to be much less than the time it takes to solve with the classical computer for a problem of a given size. And so that crossover point, that problem size where I see quantum advantage is a big question. And this is just what you were raising is, well, what's the problem I'm looking at and what's the problem size where I think quantum advantage exists? Now, there's many other ways to try to interpret that, but generally we have some best-in-class conventional method that we're comparing to. But a practical concern is whether or not this answer is actually pushing us forward in terms of the science itself. So I'll give you an example of what I mean here. So here at Oak Ridge, back in 2018, 2019, we worked with Google on what became known as this quantum supremacy experiment. And a couple people have talked about it here. And at the time, Google was using their Sycamore processor. It's a 54-qubit transmon technology laid out in a square lattice, and they were running random quantum circuits. And literally mean they would reach into a bag and pull out 1 and 2 qubit gates randomly and assemble them together, and they would run those circuits on the device, they would measure it, and they would see some distribution of outcomes. And then they would ask, can your classical supercomputer estimate what that distribution of outcomes should be? And they would compare the two. And what happened is that after a certain while, as the size of those circuits got deeper and deeper, so this index M on the bottom, the supercomputer could not keep up. It was taking longer and longer to compute those probabilities, even though they were using the best methods they had at the time, as well as the best machine they had at the time. And by the time they were done, it was at the point where the Google processor was able to solve a problem, and I don't remember the exact depth, but it was on the order of between 10 or 12 in 300 seconds. And the supercomputer was going to take probably about 100 years. And at that point, they said, okay, we have evidence that quantum computers can outperform any conventional computer on the planet. And that lasted for about a week because people immediately started asking, are there better ways to analyze the structure of these circuits and the information that you're looking for in this particular benchmark in order to accelerate that comparison? Okay, so it was a good diagnostic. I would say one of the things that actually came from the paper as well was that we had a very good understanding of the hardware, and we knew how it could be designed so that only 1 and 2 qubit interactions were needed to design it. That was also an important milestone, but it's not the one that got you the headline. Just 2 weeks ago, Quantinuum actually extended these ideas on their ion trap device, where they greatly increased the depth at which they could perform these calculations and went well past where we think conventional computers can solve them. So it's still a good benchmark, but there's still questions about, okay, but what's the scientific value of this? It's not a chemistry problem. It's not factoring. So this question of trying to find value creation from quantum computing continues to be an important part of what's going on. And you can see this actually comes from a report you can see online where it looked at what are the UN's sustainable development goals and how do these different applications map over into those. And there's a lot of space you can see here where many of the algorithms we're talking about would have impact. So a major effort right now in the field is to try and find out where can we intersect in applications, where can we create a quantum application that has meaningful value creation and demonstrates quantum advantage. Oh, yeah, I'm sure. Oh, wow, that's a great one. So this is actually a really good story behind nitrogen fixation. So the question is, how does quantum computing help nitrogen fixation? And for those who don't remember or know, nitrogen fixation is this idea that many of the living materials around us, plants, trees, shrubs, they depend on nitrogen as a source of fertilizer. It's how they create energy and can grow. And there are bacteria that actually live in the ground that can convert atmospheric nitrogen into ammonia, and that ammonia can then be synthesized by these organisms as part of their life cycle. And it all happens at standard temperature and pressure. Humans also try to create ammonia, and they do that using something called the Haber-Bosch process. And it's a very intensive, high temperature, energy intensive process. I think the last number I saw, the planet uses about 5% of its natural gas supply simply to create ammonia, because ammonia is what we use for fertilizer, and fertilizer is what we use for crop yields, and crop yields is how we feed ourselves. So the reason we don't do it the way plants do it is because there is a catalyst called nitrogenase, which has a molybdenum atom in it. And it's a very complex chemical reaction that's responsible for the conversion process. And being able to model that process with accuracy. So this is just like we were talking earlier, a chemistry problem where we expect the energy transition through the reaction process to be complicated. We would gain insights into how nitrogenase itself works, and therefore develop our own artificial catalyst for creating ammonia. Exactly right, yeah. So that's the short version. But it's a really exciting story because you can now say that quantum computing is responsible for food security, which gets people's attention. Yes, something. Can I use a real quantum device or can I use a quantum simulator for solving these problems? Yeah, for quantum advantage. So this is a tricky question. Can I use a quantum simulator, and by this you mean like a numerical simulator on conventional computer, to demonstrate quantum advantage? And my argument here would be no, because I'm using the quantum problem, but I'm running it on the classical computer. So the advantage in this case goes to the classical system. Now, the classical system, though, I would want to compare to my quantum simulator itself, like the real device, to see which one took longer, used more energy, or was more accurate. So in this case, I may not see my classical system get advantage, but using just the classical system by itself, I wouldn't call this quantum advantage. Okay, so now that we're done with the introduction, let's talk about quantum high-performance computing systems. And we've set up this idea that we're looking for value creation. We're trying to find algorithms that can use quantum mechanics that can solve problems that are interesting. In order to do that, we're going to have to integrate together our conventional computing technologies and our quantum technologies. And the reason for that is our quantum algorithms are always going to have an input to them. Even if it's just setting the register state to 0, something has to tell it to do that, and that's going to be a classical computer. Conversely, when we perform readout, the processing of that information to gain insight into the answer that we're looking for will also be a classical decision process. The quantum piece is there in the middle to help us manage the problem itself. But can we do that? Are these actually compatible with each other? They are fundamentally different platforms for performing computation. It's true that classical logic is a subset of quantum logic. Just take the classical limit. But the fact is, the way we build those technologies and the way we operate them right now is very, very different. So there's different ways you can imagine putting these things together. That's what you see in these diagrams. The question then, I'll focus on this middle one because that may seem most obvious, is that I have a network of conventional computers. These are the things called nodes. And I'm going to attach to them a QPU, a quantum processing unit, that's responsible for taking quantum programs and executing them and returning results. I can also imagine those quantum processing units themselves are able to talk to each other with a quantum interconnect. But this type of architecture plays an important decision in the algorithms that we were talking about earlier. Remember, it's algorithms and architecture coming together. Now, the node itself, I can break apart into different components. So just like we were looking at the frontier spec for their nodes, there'll be a CPU, some memory, maybe there's a GPU, maybe there's a network interface card, a NIC. But then I'll have this QPU component, the quantum processing unit, which has its own pieces inside. A quantum control unit, which is responsible for accepting input and returning output. A quantum execution unit, which is responsible for issuing instructions to the register. And the register where the information itself is stored. Today's physics experiments are already starting to look like this node model. So you can see an example here of a schematic of someone's experiments. This was from several years ago, working on a superconducting technology. And so this big cylinder over here represents the refrigerator that's housing these devices that have all been cooled down to millikelvin temperatures. That device, the actual transmons, is the register. All the infrastructure around it is responsible for maintaining the thermodynamic control of the system. The wires coming in there are connecting to these arbitrary waveform generators, the digital analog converters, and other types of electronic devices that are responsible for managing signals, classical analog signals, that are going into the register and coming back out. And if you're taking the kickboard class right now, this is exactly where the kickboard is sitting in there. It's managing a lot of the signals that are responsible for performing operations on the register, and it provides some interface to the quantum control unit, which actually runs the digital program and does the issuing of commands to convert to analog. This is a more realistic picture where, again, bottom of the refrigerator is the register, in the back are the waveform generators, and the conventional computers responsible for the control units. This is a more recent breakout. In this particular case, They're using an FPGA as well. It's not the Xilinx board that the kit class is looking at, but it is the similar design. And you can see over here the PC responsible for connecting to that. And they're not all for superconducting solid state technologies. You can also look at this in the perspective of ion trapped or photonic technologies. In this case, the QCU is represented by the PC and its network up here. The register is this trap module that is containing the ions in their service trap. And then all of these optics and fiber switches are part of the execution unit themselves. Now, in between all of those components, there are signals going back and forth. Remember earlier we talked about megahertz and gigahertz and the time scales of these technologies. That plays an important role in what the signals look like, both in terms of their time, how long they have to be in terms of nanoseconds or microseconds, as well as the shape, and you can get into more details in this reference. When I put this node diagram down with this hierarchy of languages for programming the systems, I get what is called a sequence diagram. And so over here, I have a CPU, and I type my Go quantum program. It gets loaded into the CPU's memory. It starts performing instructions, processing those. And one of those is going to be issue an instruction to the quantum processing unit through the QCU. There's a memory system that's responsible for that. And this could be a direct connection. So if you know, like these PCI Express cards, so if you've ever seen a GPU and you plug it into your motherboard, that type of memory bus is what I'm talking about here. That's responsible for transferring information. The quantum control unit then itself has to parse out these instructions and issue the operands to the QEUs. Those are then applying fields, right? So here's the switch from digital representation to analog. So now I'm gone to analog. I'm solving Schrodinger's equation on my register. I'm using the analog fields to drive the Hamiltonian. That will then collect fields coming back. Again, these could be microwaves, they could be optical signals. Many different types of analog fields can come back, but that is how I get measurement results. Dave. So it's going to depend. I'm going to actually, that's the next slide. I'll show you this in just a second. You're exactly right. So when I issue these operands, I could be, I'm normally doing them in sequence. So there are a lot of them happening right after each other. They're performing these transformations and then they're coming back. I then process that and send it back to my CPU. And that's how my CPU-QPU interaction works. That's how I start building a quantum HPC system, is I figure out how I program the QPU and actually get data out of it. But like was just mentioned, there are timescales associated with each of these steps. Conventional control systems today are all operating on gigahertz timescales. So that is, they're making processing things nanoseconds time. That includes the CPU that's issuing an instruction and the control unit. But the execution unit may actually be on megahertz scale depending on the technology. So it may take, it may have longer waveforms, which means that it's parsing those waveforms over longer amounts of time. And so you can see there's a difference of 1,000-fold between these two timescales. Similarly, the reason that's driving that is the register itself has coherence times, decoherence times, that could be on the order of microseconds, milliseconds, or longer. And it depends on the technology. So whichever technology I pick ultimately impacts the design of my interactions. But here's something interesting. If I'm using gigahertz technology here and gigahertz technology here, that's very tightly integrated. I have to measure and resolve measurements at the same time scale as which I'm losing information. This is what superconducting and semiconducting technology works on, gigahertz timescales. If I'm looking at ion traps, they're actually on megahertz timescales. I get 1,000-fold more time to process that information, but it takes 1,000-fold longer to complete a program. So there's trade-offs. Now, with that model in mind, you can create a programming stack. So this is how my application level libraries will represent data and methods. So the algorithms we were talking about earlier, how do I actually express solving a chemistry problem? There's an enormous number of packages out there today in order to do that. If I want to use quantum methods for that, I have to integrate them in. You know, especially within the HPC world, there's a chemistry package called NWChem, very popular. In fact, there's new versions of it now as well, ExaChem, that can be used for designing applications that run on HPC systems for solving chemistry. But what if I want to integrate that with quantum? I cannot just throw NWChem out, right? There's too much methodology, too much standard knowledge built into that. So this is about adopting quantum technology with our current infrastructure to see it succeed. And of course, many levels of development that go beneath that, including the circuits, the gates, the devices themselves, the execution units, and then the analog controls that are responsible for driving the register. Now, here's an example, just to give you a really clear version of how we think about this here. If I want to write a program, I'll have some source code, and we have a framework called XACC, which is kind of C++ based. In that source code, I have a main function. Within that main function, I have a subroutine that I refer to as a kernel. This kernel is going to be a representation of quantum execution that I'm going to eventually push over to my QPU. At the level of writing the program, though, I simply put out, hey, here's this prefix QPU that indicates that's where this part of the program goes. So when I'm reasoning about how the program works, I'm aware of the architecture. I know there's a quantum processor. Maybe I know there's multiple quantum processors. But how I use that is my choice, my creativity in the algorithm design. When I compile that, I actually create separate object files. So these are things that my CPU understands how to parse. And when it does that, it knows which resource to give them to. Do I give that to the GPU? Do I give that to the network? Do I give that to the QPU? But by creating this framework, we're actually able now to write programs in different languages, compile them, and then send them to different hardware. Remember, there's many different technologies out there, and they don't all use the same language for programming them. So the frameworks that we're focused on here at Oak Ridge is, how do I write a program that I can run anywhere? And it's hybrid, and it makes the best use of all those resources. Now, in addition to that interaction between the CPU and the QPU, there's the memory that we were talking about earlier. And then there's the bigger environment. Here's my application framework that will depend on system libraries. Something's responsible for scheduling that. On an HPC system, it's a multi-user environment. So you're not the only person running a job. You're not the only person trying to get access to the QPU. Something's responsible for making sure that everybody's coordinated. Now, earlier we were talking about these three architectures. Here's some indications of them. The one that is perhaps already happening today is the serial computing model, where with your laptop, you log into IBM Quantum. I think when Nick and Bibik were here, this is what you were doing. And then you hit run on your program, and it sends it over to the QPU. It performs that calculation, and it comes back to you. And this right here is actually a memory system. It just happens to be the internet. But in order to scale that up, we're actually going to have to create systems where individual nodes are responsible for managing interactions with their QPUs. And this is going to require us to decompose our program across parallel devices. Now, there's another version of this where I try to parallelize things, but I still keep a quantum interaction between them. Talk a little bit about that in a second. But the point here is that these different choices of architecture make a big difference on how I write that program that we were just looking at. So for example, we talked earlier about how do I know to parallelize my program? And there's a methodology that's called domain decomposition, which is I look at my program and I ask, well, what part of this can I divide up into subdomains? And then I can allocate those subdomains to different processors. In this case, quantum processors. Remember, Amdahl's law, though, says there's a limit to exactly how useful that will be. So the number of processors I have will have to determine what's the actual available speed up, but it's not infinite. Well, in the quantum case, it's a little more subtle, because when I decompose my domain, I'm actually cutting my Hilbert space down. So I have one QPU with n times q qubits. I could build that monolithic system, but I get no parallelization. On the other hand, I can break that up into n QPUs that each have 2 to the q qubits. I can now do things parallel-wise. But the Hilbert space of each QPU is exponentially smaller. Is that an advantage? And I don't mean the quantum advantage sense, I mean like from a programming perspective. Do I win when I do that? Do not know the answer to this question. Quantum algorithms, when they were developed, were based around this idea of a monolithic architecture where you could access any QPU at any quantum register at any time you wanted. But the reality is, in order to control these complex systems, to scale them up to sizes where we can get quantum advantage, remember, billions of qubits, it cannot be a monolithic architecture. That's too complex to design. Similarly, if I add this quantum interconnect, I'm going to have messaging between the individual nodes. Without the interconnect, I really just have to message back to like a central program that's responsible for coordinating everything. But if I'm sharing entanglement across quantum devices, each quantum device has to talk to every other quantum device in order to share information about the entangled state. So that correlation gives me an advantage, but it comes at a cost of increased communication. Now, something else that we're working on, this is a major collaboration. I think there's over 100 authors on this paper that's just come out about quantum-centric supercomputing, is how do you integrate the resource management itself into the big HPC ecosystem. So over here, you have these QPUs, there's an interface to them, the scheduler and other pieces are stored inside the HPC system. Again, it's a multi-user environment and you're coordinating access to all of those. Scheduling then also becomes interesting because I have different time scales for things that have to be completed. Some things have to be done immediately, measurement. I cannot wait to do measurement because my system's decohering. That has to happen in real time with my circuit execution. On the long time scale is the pre and post processing of the problem. Maybe I'm solving the integrals needed to create the Hamiltonian that I want to perform my simulation with, or I'm compiling the program that I want to run to make it as efficient as possible. And in between that, there's some classical hybrid algorithm concerns about what if I'm tuning things? What if I'm doing variational methods and I'm searching for the best angle? All of that's going to happen on a different time scale. Now, in the end, the way we will evaluate the performance of these systems is similar to how we evaluate the performance of systems today. Things like area actually represent how much space does it take, both in terms of the complexity of the programs that we're trying to solve, so how much space in memory, but then just actual physical space. Error, what's the logical error rate? Because if I can create a logical error rate that's very, very low, I can solve problems that are bigger and harder. Latency, how quickly is information generated by the system? Again, this goes back to system clock speed. If I'm operating at megahertz, I'm generating samples, measurement results from my circuits at probably like, one every microsecond. Whereas if I'm at gigahertz, I'm doing that much faster. But it's harder to control gigahertz systems, so my noise may actually go up. So this latency, logical error rate are going to be coupled. Accuracy, what's the actual accuracy that I get, as well as the precision? People like to talk about expectation value and observables, but another important part is the variance and the standard error. I can get an expectation value, but if my error bars are twice the size of the universe, it's not very helpful. So I'm going to have to take a certain number of samples to reduce those error bars. Well, that's going to increase the latency. Time to solution is tied to that as well. And then power, which we've already talked about. What's interesting about quantum technologies is you're controlling an individual electron in most cases. Other cases, it's a single photon. It takes a minuscule amount of energy to make an electron do something. So on a register level, we can get very low energy consumption. Our quantum algorithms say we can solve these problems using fewer operations. If I put those two factors together, I should be producing less energy or using less energy in these systems. But on the flip side, I have this overhead for fault tolerance and quantum error correction. which is 100 to 1,000-fold. So what's going to be the case in the end? Still have to do that analysis. In fact, people are doing this right now. So around the world, people are installing quantum computers in HPC systems in order to investigate these questions. And there's just a few of the examples that you can see. Here at Oak Ridge, we actually have something called the Quantum Computing User Program, where we are accessing these systems remotely and connecting them to our high-performance computing systems. And so that monolithic architecture we were talking about earlier is being dominated by this access, but we're moving over into this parallelized version as well. What's cool about this program, it's called QCup, is that if you go to the website, you can actually apply to get access to these resources as well. So we use IBM, Quantinuum, IonQ, Rigetti, all these different technologies. If you provide a proposal, that proposal is ranked highly, you actually can get 6 to 12 months of time running on those systems. So if that's something that interests you, talk to me afterwards. Okay, so this is the last slide. And I want to go back to what I hoped you learned, which was the motivation. So again, energy efficient computation, where we create value for quantum computing. That's why we want to connect quantum and HPC together. Looking for that quantum advantage application that can surpass our best conventional methods. We want to also be able to understand how we best describe the algorithms when we're working with these architectures. So there's many different variations of technology, but how we integrate those technologies will also be different. And that's going to drive how the algorithms themselves need to behave. And then metrics for testing and evaluation of systems performance. Okay, so I literally have 20 seconds left, so I'll stop. I'll take a question or two before we do our break. Station. Are there quantum computers on site? We actually have quantum optical computing here. Our next speaker, Claire Marviny, will talk a little bit about quantum optics. So I think she'll touch on this. But we do not have commercial quantum computing systems here at Oak Ridge. Abhishek.
So there was a slide where you had a syntax like C++ with, and so is that available to everyone to use?
That's an open source software. XACC is online. There's a GitHub version. Check in with me. I'll find you the most updated link for that. Claire, were you going to add something? Oh, say. Awesome. Yeah, I'm in.
How do you envision the big for like these devices and fault tolerant stuff? So it's just like a module that I can plug in for the tool chain, such that I can sort of dispatch the fault tolerant, because there is a lot of different problems.
Yeah.
Is there a tool chain sort of?
Yeah, good question. So the question was, how are we going to integrate fault tolerance into quantum computing programming stacks? And right now, a lot of what we're doing is focused on NIST devices, which don't have fault tolerance built into them. I think it's going to be an evolutionary process. I think we're going to start writing programs that try to integrate error correction and fault tolerant capabilities into the programs themselves. And then we'll see people testing those on devices now. But in the long term, I expect that the error correction aspect will be below the user level. So the vendor will be responsible for creating quantum execution units that actually perform error correction and fault tolerance, so that the user does not need to worry about this. In the same way that you don't need to worry about the transistor sequences that are driving the GPU performance now, you only have a high-level programming interface. But getting to that state is going to require a lot of research and development along the way. Anastasia?
Is that for schedule of quantum computing competition? Do you or does anyone create a completely new scheduling system, or they build on top of the?
Yeah, that's a good question. So for scheduling on the integration of HPC and quantum computing systems, what are the tools available there? It's going to depend a little bit on what level of scheduling. At the systems level, there are tools like Slurm and some others that are good for managing jobs that are running. And those jobs, in some sense, Doesn't matter if they're quantum or not, they have to be managed at that level. What we are finding is that one of the unique aspects is that, especially for remote access, there is a separate scheduler for remote access in the networking, and that can't keep going. That's a bottleneck in performance. So I do think that high performance systems require on-premise access, and that the scheduler then at the resource level has to be designed specifically for quantum. Yeah.
With parallel particular problem. With all that mathematics stuff, maybe applied for quantum computing.
Yeah, good question. So the question is, can I translate over a lot of the conventional parallel algorithm design to this distributed quantum computing design? And this is a hot topic. If I'm using the QPUs as independent accelerators, then sure, I can take like my partial differential equation that's maybe using a method of partitioning problems across grids and solving each independent mesh or grid using a quantum processor to try to accelerate that. But is that the best way to do that? Because if we go back to this problem of decomposing our Hilbert space, we may be losing an opportunity. So I think you can do that. I think it's straightforward, but the question of whether it's really the best method in the long term, this is open research question. Yeah. Yeah, so the question is, what's the state of the quantum interconnects, especially between QPUs, right? Yeah, so talking between quantum processors is open research area as well, and it depends on technology. So for some of the ion trap technology, they're easily addressed using optical links. So it's certainly possible to connect optical ion traps together optically. And there's been a few experimental demonstrations of this, but nothing in a production scale that I know of, or even in like a testbed scale. But the interconnection of, say, transmon technologies actually requires solving a transduction problem, which is to convert the signal, that analog signal we were talking about, from the microwave domain into the optical domain, because you have to transverse out of the refrigerator, across the room into the next refrigerator. And so that transduction process can be inefficient and you can lose information. So it's another source of decoherence and information loss. So there's a lot of people looking at transduction as well. And all the technologies are in similar state. Okay, let me make this the last question because then we'll take our break, and I'm happy to talk in between the break. But the question is, what's the state of translating existing libraries like linear algebra? Think about like LinPack, it's a well-known linear algebra package, using quantum methods. I would say it's very early because on the one hand, the quantum algorithms themselves may indicate an advantage for use them only at a very large size. And people are still trying to evaluate, well, where's the applications where I need that size? In the near term, actually testing those devices is encumbered by the noise in these systems. So being able to get fault tolerance and error correction may be a requisite, required before those libraries could actually be successful. So it's in an odd place right now where the technology itself isn't quite ready for that testing, but there's lots of research into looking at how to test that. So. Okay, folks, so let me take a break there. We'll take our break now. Oh yeah, thank you very much. Thank you very much. You guys like this, wait till you see your next speaker. So that'll be in about 25 minutes. We'll start at 10:45. Everybody take a break and we'll see you back then. Thanks.